Okay, welcome. Today I'd like to talk about how we model population dynamics subject to stochasticity. And the way that which we're going to do this is through what's called a Galton-Watson branching process. Okay, and the stochastic process that the Galton-Watson process models is one of two types of stochasticity. And the two types of stochasticity that affect population dynamics are environmental stochasticity and this is, stuff like rainfall, temperature, wind, things like that, things that affect identical individuals identically. Okay, and so, and this is generally when we think about population level models. This is generally the type of stochasticity that we model into, say, a difference equation or a differential equation. But there's another type of stochasticity, and that's what the Galton-Watson process models, which is demographic stochasticity. And this is the stochasticity that affects otherwise identical individuals differently through individual variability. So you have, for example, identical twins, and of course their lives are not identical. They generally don't have children at this exact same time. They generally don't die at the exact same time. They might not even grow to be the same size, and so forth. And that's, a tricky thing to model because you have to model at the individual level, and a lot of our traditional mathematical biology models do not do so. They work at the aggregate level. Okay, so and branching process models are of various depths and simplicities and complexities. And so we're going to start with the most simple version of this, which again is the Galton-Watson process, which got its origination through trying to study the likelihood of the extinction of a family name. So here's sort of where we're going to start here. Consider a population of males with a given surname. Now we're sort of making the somewhat archaic assumption that surnames are passed via the male, but that's the assumption that we're going to make. And let X subscript T be the number of such males in the population during the 10th generation. Okay, so again, if you start out with somebody's grandfather, for example, they're in the second generation in this case, and so that's where we're going to start. Okay, assume an individual has I offspring with probability P sub I. Okay, and what do these probabilities sort of have? Well, we know P sub I needs to be greater than or equal to 0 for all I equaling 0, 1, 2. There's a possibility to have sort of an unbounded number of offspring, but of course those probabilities are super low, and you can't have fewer than 0 offsprings. And then we know that if you sum all of these probabilities together, you end up with 1, right? Because one of those outcomes has to occur. Okay? The next assumption that we're going to make is that individuals, and this is a big assumption, and it's generally violated in practice, but we're going to assume that each male has an offspring success that is independent and identically distributed throughout his family. Okay, so a father has the same offspring distribution as his sons, who have the same offspring distribution as their sons, and so forth. And each individual's offspring success is independent of his brothers, his fathers, his uncles, things like that. This is probably, because we've had birth rates that have varied we have varied in the past. This is probably a bad assumption, but it's mathematically advantageous to have this assumption. And so that's where we get to our sort of main object here. So our main object is the E sub t, which is the probability that the population of males is equal to 0 given the initial population started with one individual with that surname. Okay, so let's say that you're the only individual left in your family with a given surname. What's the probability that in T generations your name is extinct? That's what we're going to be looking at with the Galton-Watson branching process. And the way that we're going to study this is iteratively. Okay, so note, and this is where we set up our mathematical model, the probability of going extinct as a family name in T generations really does depend upon, well, if you have 0 offspring, okay, your family name is extinct. If you have 1 offspring, and then your offspring takes T minus 1 years to cause an extinction, that's an extinction event. If you have 2 offspring, and then those 2 individuals cause an extinction in T minus 1 generations, well, we have to square that probability, okay? And we continue in this way. Right, so if you have 3 offspring, and all 3 of them cause, eventual extinction of your family name in T minus 1 generations, and that's a cube, and you continue in that direction. And what you end up having, okay, because your population is not extinct when you start the experiment, you have an initial condition of 0, and you have this difference equation, whereas if we call this right-hand side f of E sub t minus 1, you have this nonlinear difference equation for the extinction probability of your family name. So this is your Galton-Watson branching process model. Notice here at this f, if you've taken a statistics course, this is a moment generating function. Moment generating function of the set of probabilities that govern your offspring success. Okay, so that's an MGF. It generates all the moments for your offspring. So the average number of individuals reproduced by an individual in each generation, the variance of such outcomes, and so forth. Okay? Now, once we have this, again, the sequence E sub t as t goes from 0 to infinity is the sequence of extinction probabilities for a given surname. while if we take the probabilistic complement, so 1 minus e of t, this is the sequence of persistence probabilities for a given surname. Okay? And in the next video, we're going to talk about actually how to compute some properties of this extinction probability. But before I leave you, I want to tell you why it's called a branching process. And that's sort of the question here. So why a branching process? And the answer, I think you can imagine if you have some background in probability, you know, this whole thing starts with one individual, okay, and they'll have 0 offspring with a certain probability. They'll have 1 offspring with a certain probability. They'll have 2 offspring with another probability, and so forth. Okay, and then each one of those individuals has sort of the same structure. So 0 offspring with a certain probability, 1 offspring with another probability, and then each one of these individuals again has their own branches. So P0, P1, right? And what you end up with is branches. Okay, and again, hence the name branching process. Okay, thank you.